It is a great honor to introduce Dr. Daniel Moraro, an eminent researcher and academician whose pioneering contributions have significantly advanced the frontiers of nano device technology. Dr. Professor in the Department of Electronics and Material Science at Shizuoka University, Japan. He earned his doctorate in nanovision science and technology from the same university and subsequently deepened his expertise as a postdoctoral researcher at the Research Institute of Electronics. With over 2 decades of academic and research excellence, Dr. Moraro has made remarkable contributions to silicon nanostructures, single electron tunneling, and dopant-based electronics. His prolific body of work includes over 200 peer-reviewed publications, contributions to international book chapters, and more than 50 invited and plenary talks delivered at leading global conferences. His pioneering research has earned him numerous accolades, including Japan Society of Applied Physics Silicon Technology Division Paper Awards, the Takayangi Kinjo Research Encouragement Award, and the prestigious IUMRS ICEM Young Scientist Gold Award. Please join me in welcoming Dr. Daniel Moraro, a scientist, a passionate educator, and an inspiring leader in the field of nanotechnology. Now, I invite Dr. Daniel Moraro, Professor, to take over the session. Please, sir.
Thank you very much for the kind introduction. I hope you can hear me. Everything is fine?
Yes, sir.
Yes, sir.
Thank you. It is a great honor for me and a pleasure to be introduced so kindly. So thank you very much. Let me share the screen now. I'd like to confirm if you can see the screen.
Yes, sir. We can see that.
You can see the full screen and my laser pointer as well, right?
Yes, sir. Yes, sir.
Okay, so maybe for I will just switch off the camera for the convenience of transmission. Okay, so first of all, many thanks for the invitation to give a talk in this very nice event, and I'm learning a lot about the faculty development program, well, and about the coordination from SRM, Institute of Science and Technology. It's always a pleasure to be a contributor to any event organized from SRM. And just as a preview, I will be in Chennai actually in October and November, visiting there. So hopefully I'll meet many of you face to face on that period.
Sure, sir. Sure, sir.
So today I will talk, as introduced earlier very kindly, about nanometer scale electronic and photonic devices. Maybe what I can add to this is that these are in our lab developed in silicon. So we are still keeping the CMOS compatibility, and we hope to bring some new physics into the electronics in the future and into photonics as well. If you are interested in what we are doing, you can scan these QR codes on the corners. This takes you to my homepage as well as to my database for research. So you also heard that I belong to the Research Institute of Electronics. You are always welcome to visit us here, and actually I will start from a short promotion of our faculty so that many of you can actually join us and visit us in the future, either at the Institute or at the Faculty of Engineering, to which I also belong. So let me start with a short introduction from about my background. I'm obviously not from Japan. I'm from Romania, which is actually a country in the Eastern Europe. Maybe many of you are familiar now with that area because of the Ukraine situation. I graduated from Faculty of Physics and both bachelor and master course, and I also taught physics in high school for a while, which was actually a very inspiring period for me to trigger more curiosity into science. Then I came to Japan, and at that time, I joined Shizuoka University for taking a PhD course in nanovision science. There's the combination between nanoscience, nanotechnology, and optics, photonics, optoelectronics. And then I continued through different stages, and I'm currently a full professor at Shizuoka University. I have also been for a very short time in Australia, visiting professor at Swinburne University of Technology, carrying some, let's say, boundary research between silicon nanodevices and laser processing. And I'm also currently an executive director at the JSAP, Japan Society of Applied Physics. And especially I'm in charge of diversity and inclusion as well as international relations. So this is a very good entrance point into the Japanese academic and research society. So I strongly encourage you, if you are interested, to join one of these events in the future. As I mentioned before, I've been also a visiting professor at SRM for a while, and I will come back again quite soon. And hopefully I will have a chance to meet you on campus as well, or in other occasions. So let me very briefly introduce the Shizuoka University, although probably many of you are familiar with this institution. It's actually in the middle of Japan, and it's a national university, not very large, about 10,000 students, 1,100 staff, but actually quite flexible from that point of view. And we have two campuses, Shizuoka for the basic science, but also we have a very good view of Mount Fuji, if you prefer that. And on the other hand, we have Hamamatsu, which is a campus containing Faculty of Engineering and Faculty of Informatics. It is connected actually to the very large industry of Hamamatsu City, and I will introduce that next. We have various programs connecting you to European partners, and also we have a program called Asia Bridge Program. Many of the students, of your students, could be interested to join master course. Tuition fee exempted. So you have 2 years master course based on this program. So these are just a few snapshots for promotional material of Shizuoka Prefecture. I strongly recommend it to come and visit. Green tea is very popular here. So that's just a promotion before we enter into the serious part of our talk. The last promotion I want to make is about the city of Hamamatsu, where I'm located. It is known as a city of industry as well as a city of music. And you may find here several very famous companies, international companies that are actually headquartered in Hamamatsu. And Yamaha, Suzuki, Honda, Roland are all located here, Hamamatsu Photonics as well. And the research related to photonics, by the way, this is a video of our research institute in the night, all started from the work of Professor Kenjiro Takayanagi, who developed the all-electrical TV. So Shizuoka University is seen as the birthplace of television in Japan practically 100 years ago. So this is the background of where we are, what we are doing, what is our history, let's say. Hopefully you come and see by yourself in the future. So now, with this message as a final message, let me move to the scientific part of my talk. So I have an outline given here, which will actually take you through a relatively long series of topics. One is, how did we reach the situation that we can now look at atomic level electronics from the moment of the invention of a transistor? This is a little bit of historical short overview of what happened in the meanwhile. The basic concept that we use in our lab is actually to transform dopants or impurities with which you may be familiar from semiconductor physics, from solid state physics as charge providers. We want to repurpose them to become quantum dots. And with this, we create a variety of new device concepts. We are basically working on device level, and we can fabricate and characterize devices such as silicon nanotransistors or silicon nanodiodes. And generally, in the recent years, we are working on multiple dopant quantum dots, but it all starts from the idea that one dopant atom can work as a quantum dot. So I will explain that, and then I'll go through a few topics related to each type of device. At the end, I will show how we can use these devices, which have a capability to flow single electron tunneling currents, for detecting even single photons. So that kind of photon detection is another aspect which brings us to the photonics. So let me start with the first very brief historical introduction. Of course, we are very much aware of the importance of integrated circuits in our daily life. This is one of a version of many, many slides that can reveal how electronics affects all aspects of our lives, from communication to storing of data, wireless and smartphones, satellite GPS, anything is now affected by the capabilities of the integrated circuits, which are at the core of any computer. But behind the integrated circuits is the invention of the transistor. And here is a probably very famous snapshot from about 80 years ago of John Bardeen, William Brattain, and Walter Brattain and William Shockley, who actually co-invented the transistor. And that was, in a way, a breakthrough, moving away from the as you may know, the vacuum tubes that were used as switches. The transistor was not very beautiful. It was just a piece of semiconductor in contact with a piece of metal, but it worked as an on-off switch. And it was enough to trigger further development. Now you are very much familiar with this kind of view. You may have a source and a drain, let's say N-type, and a channel which is P-type, with its potential controlled by the gate. That's a MOSFET, metal oxide semiconductor field effect transistor. Now, this in billions and billions is connected inside a 1 centimeter by 1 centimeter chip, and it provides us the functionality that we actually benefit from nowadays. So, historically speaking, we should treat the transistor demonstration as a trigger to information age, and what followed next was very famous, the continuous miniaturization along the Moore's law, the Gordon Moore being the Intel CEO at that time in the 1960s. So this view is very famous. The horizontal axis shows the year, vertical axis shows either transistor density, or on the right, the minimum feature size, the gate length typically. So as you may see, in the 1970s to 1990s, practically Intel was the leader and the pioneer in the field of electronics, and these integrated circuits contained basically not this kind of transistors, of course, refined transistors, but just a few hundreds or thousands of transistors with dimensions on the order of micrometer. But then things were developed so much by competition and by manufacturing improvements that nowadays, it's a little bit outdated, this figure, but nowadays we are certainly having gate lengths below 10 nanometers in our computers, actually. And that allows us to pack a lot of information into a very small area. Nowadays, or maybe even less, a few years ago, the 22 nanometer node brought us also to some vertical scaling, and this also helps to push this law further and further. However, we are all aware that we are reaching the physical limits, and in my lab, as what we see about the next generations of electronics, since this is the purpose of this training as well. Well, in my view, we'd like to use electrons one by one. So ideally, we want to take a low power consumption from these devices. A compact design should be also expected. So every atom counts, and we want to involve fundamental physics, especially quantum mechanics, which is not sufficiently included into current operation of transistors. We also want to keep CMOS compatibility for many reasons, including costs, but also including advanced technologies. So with this in mind, my lab's view is to attack the problem of controlling single electron tunneling in silicon nano devices as one of the new mechanisms for the next generations of electronics. So how we will do that, I will explain in the next slides. But first, let me introduce the vision that JSAP, Japan Society of Applied Physics, has about the Moore's law. Practically over the few decades, the CMOS technology has been pushing the dimensions of the transistors to lower and lower values. In the past decade, we were working with transistors which were a few tens of nanometers in size. Nowadays, we are in the middle of this decade. We are actually at scales of 5 nanometers as a technology node. And that means we are moving towards one-dimensional transistors, resonant tunneling devices, and it is envisioned that single electron devices will also play a role in this decade, let's say. Furthermore, we are going to move into the single-digit nanometer deeper and deeper up to even atomic level. And that's where we are meeting the barriers or the fundamental limits of pushing further electronics based on the simple CMOS technology. JSAP also has a duty to provide social impact of this kind of technologies, and you can see here some of a vision of this society to which I also belong. By the way, this is being upgraded. Hopefully, we will show you soon a new version of this map, because many things are changing very rapidly nowadays, including machine learning and artificial intelligence and other things that were not included at that time. So let me now move to the basic concept of our research, and that is how dopants or impurities work as quantum dots. Now, the dream that we have in our lab, let's say, by the time I retire, is to utilize an active atom and make the entire current and the entire operation of a device flow through this active atom. However, it cannot be suspended in vacuum, so we do need nanotechnology in the future to embed this kind of active atoms into a nanostructure that can keep it in place. And also, we can actually bring the crystalline matrix of silicon as a host for this kind of active atoms, which could be substitutional foreign atoms, in other words, impurities or dopants. And those can be active atoms. We also leverage nanotechnology to build leads or electrodes nearby, and we can actually create a circuit together with a gate nearby to form a transistor as a basic idea. Now, what would be the advantages of struggling to make this device? It provides ultimately low power consumption because electrons would flow one by one into this atom and out of this atom towards the lead. It also provides fundamental physics for operation because electrons in the leads would have to tunnel into this atom and tunnel out. So quantum tunneling will be the operation mechanism. But on the other hand, it is fully CMOS compatible because it still utilizes silicon as a host material. So this is why we think that dopant-induced quantum dots could actually be very important for the future generation. So I want to change your perspective about these impurities. A dopant atom, many of you may know that it's a charge-free carrier provider. Let's say the phosphorus donor in silicon substitutionally, it modulates the potential around its nucleus on a radius called Bohr radius of about 2.5 nanometers. Now, the reason for this is that once ionized, P+, this phosphorus introduces a Coulombic potential well around this nucleus, and it has a ground state around 45 millielectron volts below the conduction band edge, which is this green line. Of course, we know the spectrum of this kind of atoms very well for tens of years by now, but what we don't perceive very clearly is that this can become a quantum dot. Once an electron is injected here, if we could avoid its thermal activation to the conduction band, we can actually move it in and out by tunneling from leads nearby, and that makes it a very good quantum dot. So here is how a device would look like. This individual dopant works as a tiny quantum dot. Let's assume that we use nanotechnology to create a source and a drain, embedding or sandwiching a very tiny channel in the middle, where by some method we could introduce one individual dopant, let's say a phosphorus, and gate it. So if we can create a structure, and I'm not going to enter into the details of how challenging this is, but I will answer to any questions later if there are. We can actually utilize the Coulombic potential well of this donor as a stepping stone between source and drain in this potential map. So if you use the gate voltage, you can tune this potential well, bring it in the way of the electrons in the reservoirs, and if you are at low temperatures, electrons would tunnel into this potential well, one electron, and then tunnel out, forming the current. While the electron is inside, another electron cannot come into the potential well because of the electron-electron repulsion force. In other words, Coulomb blockade. So that is actually the mechanism that brings us to observe in the drain current gate voltage characteristics, transfer characteristics, current peaks, especially at low temperature. These current peaks are simply illustrating the different charge states of a phosphorus donor. And on the peak, actually, as explained earlier, we can switch the charge state of a phosphorus from P plus to P0. And on the sides, you can keep it either ionized or neutralized. And that can be done with a gate voltage simply. Now, there is a single problem here. The barrier height could be at most 45 millivolts, millielectron volts, because that's how the ground state is located in a normal phosphorus donor. So why is this a problem? If you increase the temperature, the Fermi-Dirac distribution broadens, and electrons from the tail of this distribution would actually be able to move above the barrier, create a high current, and hide the single electron tunneling current that is this peak. So firmly activated carriers actually mask the current component, the single electron tunneling current component, which we are looking for. So our group is actually chasing the practical operation of these devices at room temperature if possible, and we hold the world records in this kind of operation. Let me take you through a little bit more historical view. In 2006, actually, the first report of such transport was given from Delft University of Technology. They observed that very low temperatures, that an NPN transistor actually exhibited some spikes of conductance below the threshold voltage. The reason for that was demonstrated to be a dopant atom stray or escaped from the leads from source or drain into the middle of a channel. And this kind of accidental observation of single dopants is still very practical, but it was not the intention. Later on, we also could demonstrate individual acceptors showing similar characteristics or similar modulations of a conductance in a p-type transistor. As you can see, the transistor switches on by applying more negative gate voltage, but it also shows a current peak on the side. And this all happen at low temperatures, but it shows that single dopants, either donors or acceptors, can actually modulate the current significantly. Now, what we do in our lab, and you have a QR code here for our clean room, is to utilize clean room facilities at our institute and fabricate the nano devices ourselves. So if you're interested in joining our group, for instance, you could also, or visiting us, you could also experience the full set of fabrication from wafer level. And we typically use SOI, silicon-on insulator, for its very advanced properties. And you can experience oxidation, etching, doping. All processes are carried out in the clean room. We can also use electron beam lithography, and actually we have to use this if you want nanoscale dimensionality. And with a proper resist processing, we can create structures as shown here. Nanostructures, nanowires, nanobridges, and with side gates, with top gates, with back gates, different varieties, with a lot of purposes as listed here. They can work as MOSFETs, but also as single electron tunneling transistors. They can work as PN diodes if we dope them properly, or tunnel diodes, and I will show a few examples from this type of devices. So please check our what is available in our clean room from these links if you're interested, and you can, well, hopefully in the future experience these techniques as well. This is just a view of one of the devices, but please note that we fabricate thousands of this on 1 centimeter by 1 centimeter. And the silicon-on insulator substrate contains a thick substrate silicon, buried oxide layer, and a thin layer of silicon, which can be patterned by electron beam lithography. You can see also the source, drain, and gate are covered by a metal, which is aluminum in our case, and this is also a typical biasing circuit. So what is important for our devices is that we have a very narrow and very short channel that can be developed thanks to our techniques of handling resists with electron beam lithography exposure. In terms of thickness, as shown by this TEM image, the channel can be also extremely thin, just a few nanometers or 10 nanometers with some degree of control. And you can see here a high-resolution TEM image which shows the crystalline matrix of silicon embedded into the amorphous silicon dioxide. Now, even this kind of small dimensionality capabilities are not so interesting for us. What we are interested in is the functionality that we can obtain from substitutional dopant atoms or impurity atoms and not from silicon atoms. So we should understand very clearly that we are actually building these big devices, actually microscale devices with nanoscale or hundreds of nanometer size channels in order to capture the atomic level functionalities. So to do that, we utilize an equipment called IV prober, and that allows us to measure the IV characteristics in a wide range of temperatures. It's very stable mechanically because we have a lot of weights on the bottom here. In this metallic chamber, we can make a vacuum, high vacuum with these pumps, and place our sample inside. Now, we can monitor it through this CCD camera on the screen, and we can control the temperature from, it's not seen in this image, a helium compressor to go down to even 5 Kelvin. Now, these manipulators here allow you to control very easily needles, conductive needles that can connect you to a parameter analyzer, and you can measure the current. On the right, I'm showing you another machine that we are using in our lab, Kelvin probe force microscope. This allows us to measure the electrostatic potential even due to single dopants and in a wide range of temperatures as well. Time is limited today, so I will not touch too much on this technique. I will focus only on the electrical characterization as shown here. So let me show you what we can obtain by fabricating our nano devices in nanoscale and by utilizing this kind of sophisticated techniques, let's say for IV current measurements. So what I'm showing here is actually only the snapshot, an illustration of the channel of a device, which is built in silicon on insulator. So a very thin layer of silicon. Of course, we have buried oxide below. We have thermally grown oxide on top and a gate on top. But for observing the dopant distribution, I removed everything for simplicity. So we started by doping our channels to a concentration of 10 to the power 18th per cubic centimeters, which means that the distance between two dopants is on the average 10 nanometers. Now, considering that the bore radius is about 2.5 nanometers, this is sufficient distance that the dopants are not influencing each other too much. So we can treat each of them as distinct individual dopant. So in such a channel, despite the random distribution of dopants, we may have the source and the drain bridged by several of these dopants, individual ones, and actually we measure the IV characteristics at low bias and also at low temperatures. So when we do that, we can observe in many cases, although different from device to device, current peaks, as I explained before, and these current peaks can be ascribed to different phosphorus donors. Now, each of these phosphorus donors carries the current by single electron tunneling, mainly through its ground state, and shuttling the electron towards the drain in sequential mode. And then we are measuring for a certain amount of time, we're measuring the amount of electrons passing, and that converts into current. Of course, we have some excited states, and once the electron becomes trapped into this quantum dot, it neutralizes it, and then we cannot flow any more current through this dopant. Another dopant has to take over as a current path. Now, we reported this statistically in Physical Review Letters in 2010, 15 years ago, and that was our entrance point, let's say, into the atomic level electronics, because we showed that it's a simple method to develop this kind of devices. We combine nanotechnology and uniform doping at a controllable macroscopic doping concentration, and we can still observe signatures of atomic functionalities. So what we did later was to find purpose for this kind of devices. And we think that ultimate sensing can be one of those. Let's take one example from this Applied Physics Letters publication. We actually took one of its peaks and measured it upwards and then downwards and observed that it contains, in some cases, a hysteresis of current between upward and downward sweep. And if you measure the time dependence inside this hysteresis, it switches between mainly two levels. And that switching is actually a detection using single electron tunneling through one dopant of a charge state of another dopant working as a trap. So this could be developed or converted into a memory concept which utilizes a single atom as a sensor and a single atom as a memory node. We could also use these devices under light irradiation because every single photon absorbed in this channel converts into an electron-hole pair. Now, if you have traps nearby, the electrons can be captured by these traps, and we can actually use this single electron tunneling current to sense this kind of traps. So if you compare the time dependence in dark with the one under light illumination, here we use the visible light, we can see that there is a clear dependence on the photon flux in terms of switching of a current, so-called random telegraph signals. So this kind of dependence indicates that the number of photons influences the number of electrons trapped, which subsequently influence capacitively the charge flow to the main dopant. Again, this is another APL around that time. So this was our initial statement. But please note that temperatures were relatively low. So now with this kind of background and this kind of physics, we wanted to raise the operation temperature. So to do that, we figured out that we should change the simplistic structure of a channel into a stub-shaped channel. The reason for that was that even if you have a random doping in this kind of devices, some of the dopants could be in these sharp corners and surrounding mostly by SiO2 oxide, and also affected by quantum confinement and dielectric confinement. In that case, the dopant state becomes deeper. So with that, we demonstrated that a single electron tunneling current peak can be observed in some devices even at a temperature of 100 Kelvin, and that was reported as a world record for single dopant devices in 2013 already. What you should notice here, however, is that this is not an easy current to catch. Please note the current level of this kind of peak embedded into an otherwise FET on-off switch current. The current level is just a few tens of femtoamps. So in order to detect this kind of currents, we should have the equipment and also the stability of a measurement system and the high quality of the devices. Otherwise, this is embedded completely in the noise level. So we reported our vision about single dopants and what we can do with them in this nanoscale research letter, Nano Review. And of course, we can develop transistors, we can develop memory devices with two dopants. If you have more dopants, you can build turnstiles or pumps. And as I showed earlier, optoelectronics based on dopants is also an option. And I'd like to add to that the fact that we can actually see these dopants with Kelvin probe force microscope, KFM. So if you're interested, please read what we summarized at that time, again, many years ago, as atom devices based on single dopants in silicon nanostructures. So this is already, there is a lot of development, not only from our group, but from other groups around the world in this field. Later, we realized that there is a little bit of end of a line for these single dopant devices because it's very hard to control single dopants. We introduced, therefore, a selectively doping technique that allows us to build not single phosphorus donors as quantum dots, but to couple a few phosphorus donors strongly or less strongly as a new quantum dot. So if you couple two donors together, we get a deeper potential well. If you couple three donors together, you get an even deeper potential well. In that way, this kind of a system works as a molecule but at the same time, it can allow us to move from a system with a small tunnel barrier to a system with an enhanced tunnel barrier, as shown on the right. To implement this kind of design, we utilized again nanotechnology and developed a pocket for doping dopants in the middle, simultaneously with source and drain, leaving a barrier, an undoped barrier on each side with dimensions on the order of 50 nanometers. These were not very much optimized devices, but we did hope that we can keep the potential well, as shown here, with a deeper potential here and a higher barrier on each side. So the simple process is also very important. So this is a cross-section of our devices, SOI, as I mentioned before. We do a thermal oxidation, a dry oxidation first. We then nanopattern this mask with an electron beam lithography technique. We open a pocket, a window here, and also windows for source and drain. And then we spin coat the doping source on top of this slightly oxidized surface and drive in the dopants through a thermal diffusion technique in a furnace or a rapid thermal annealing machine. And then the dopants will be introduced only in the desired positions because they cannot penetrate through this oxide mask. Nevertheless, we should be aware that there is side diffusion, so it's not a perfect process. It still needs to be optimized in the future, but it allows us to build molecules of a few phosphorus donors. We raised the doping concentration macroscopically 1 order of magnitude, 10 to the power 19th, and in that kind of conditions, statistically, we can form clusters of just a few overlapped phosphorus donors in the middle of this channel, and we have a little bit more control on the location and the structure of a device. So with this, we obtained the IV characteristics, again, at low temperatures, small source drain bias, and they look significantly different from the ones due to single dopants. Now we observe current peak envelopes, like structures, broader structures, which are also an illustration of single electron tunneling. At the valleys of these peaks, electrons are captured into this quantum dot. However, there is also some substructure embedded into these peak structures, and this, despite the noise and a little bit lack of similarity, we can ascribe to a tunneling transport spectroscopy of the dopant molecule. So in such a case, statistically, we expect that just a few donors coupled together, ground state is split into a multi-state, and then electrons can actually scan through these energy states as they are swept in front of the source Fermi level by the gate voltage. What happens next is that one electron becomes captured there, and the second electron is actually scanning the remaining spectrum, and we observe it as a substructure in the next peak envelopes. So it's a very fundamental observation of a molecule created by a few donors. The problem with this is that it's still at low temperature. So we were not successful in raising the operation temperature because the device was not optimized. However, we were successful in observing at low temperatures a lot of information about this kind of dopant molecules. So I'll show you a few more insights next, and these were obtained with my PhD student several years ago, and he measured the stability diagrams for this kind of devices. Stability diagrams means to measure the actual absolute value of current in the space defined by gate voltage and drain bias. In that case, typically we measure by applying a few tens of millivolts to the source drain bias, and we can observe noise level current up to some point, and then so-called Coulomb diamonds successively arranged at higher voltages. These are signatures of single electron tunneling being observed in our devices. However, we had a feeling that there must be something hidden in this noise level region. And for that, we increased the VD to values which are typically not measured usually. And when we measured in a wider range, we could observe actually extra Coulomb diamonds with a little bit peculiar shape, and which are not closed. These are open diamonds. They do not close at BD equals 0, and that makes them a little bit peculiar considering our expectation that a single quantum dot works in these devices. So we can at least simply split the stability diagram into two. One is the large diamonds observed at low VG, and the other zone is where we observe fine diamonds at high VG. Each of them will be explained next. So let me show you one device. For instance, this is a selectively doped SOI-FET device A. We observe this pattern is the same device that we explained earlier. And this is a zoom in on this zone of interest, zone 1. What we observe here as dashed lines are these diamonds, open diamonds that I will explain a bit later. Another device exhibits similar but different in terms of voltages and in terms of pattern behavior. But nevertheless, we have two zones, zone 1, which contains these broad open Coulomb diamonds. So the reason for this is a little bit mysterious at that time, and we couldn't explain why we observe the structures from a single quantum dot. So I will explain later how we interpret this. This quantum dot is actually in the middle between source and drain in a selectively doped region, and it gives rise to such characteristics at very low temperatures. We should note, however, that the gate voltage controls not only the potential of a quantum dot, but also the potential of the barriers themselves. So in that sense, we can actually expect that the resistances affect very much the transport. About zone 2, the situation is much simpler. These Coulomb diamonds are, as shown in the zoom-in images on the bottom, closed diamonds. It's unfortunate that these are a little bit affected by noise, but they are still clearly sequentially observed diamonds and not perfectly periodic, and that means that we may have a quantum dot array working in this kind of situation. So by that time, the gate voltage allows you to fill in this multiple donor cluster quantum dot almost completely, and we are left with only very shallow potential fluctuations, and electrons would tunnel in this way from source to drain at the higher voltages. So now let me return to how we interpret these devices. Well, if you apply the gate voltage, we are moving the potential in the channel both in the quantum dot and in its barriers. So therefore, we should be aware that the resistance, tunnel resistance, is actually dependent on the gate voltage. At the same time, what happens when you apply source drain bias? If you apply the drain voltage positively and ground the source, only the drain side barrier will move. So in that sense, we should be sensitive to the drain side barrier resistance, tunnel resistance, and its dependence on VD. So we actually introduced dependence on the parameters, resistances, RS and RD, which are the resistances on the source and drain side, to be dependent on VG or on VG and VD for the drain side. And at the same time, if you apply a reverse bias, you can actually convert or invert the source and drain. And again, you have to be careful about the dependence of the source and drain resistances on both VD and VG. So we introduced an analytical expression which allows you to modulate the resistances depending on the biases. So with that, we actually plugged it into a Monte Carlo simulator, which simulates a quantum dot coupled to source and drain through tunnel junctions. These are characterized by a capacitance and a resistance, and also with a potential controlled from the gate through a regular capacitance. So with this, we could simulate the stability diagrams again, and the yellow lines here illustrate what would happen in an ideal case when we could measure the current very precisely. We should observe closed Coulomb diamonds, equally spaced and of equal height from the consecutive addition of electrons from 0 to 5 electrons, let's say, in this range of VG. However, what we really observed was a shape like an open mouth for this device. So the reason for that is indeed the sensitivity of the resistances to this operation. So now we can understand why this structure is observed. It is because we have to add the resistance increase as we make the gate voltage more and more negative. So with that said, we can actually map out what kind of charge states exist in these channels, in these clusters. We can actually understand what charge states are actually involved in current. If you map points like M and N shown here, you can actually tunnel several electrons simultaneously through our quantum dot. So if you're interested in more about this, sorry for taking too long time to discuss this, you can go through the Applied Physics Express paper published a few years ago. So now I'd like to move to the high temperature operation of these devices. So in this kind of devices, we aimed ideally for the high temperature operation. So we spent actually the next few years until 2017, let's say, to optimize our devices in a few aspects. One was to make the pocket very, very small. So we designed it to be just 30 nanometers with a slightly bigger barrier. So even if we have a side diffusion, we can still keep these barriers undocked. A second idea was to make the nanowires very, very small, width and thickness just a few nanometers. So in that case, we have a few dopants coupled here as molecules and giving rise to a very deep potential well in the center between source and drain. And the key point here is that we are now limiting the transport paths to just one unique transport paths. So if you can do that, we have to flow the electrons exactly through one quantum dot and move it out, while transport through nearby areas is impossible. It's covered in insulator. So this work was done with Dr. Arab Samanta, now associate professor at IIT Roorkee, and he was a postdoc in my lab around that time. So with this optimized and nanostructured channel, we actually started to measure the stability diagrams. By now, hopefully you understand that this is a map of the absolute value of current in the space of VG, gate voltage, and VD. So we observe again this small Coulomb diamonds from extended quantum dots, but also we could observe the signature of a very small current observed at negative VG. Now this could be the SET via one few donor molecule, and we proved that this is actually a current peak by looking at a high temperature, 100 Kelvin, not 5.5 Kelvin as the first map. So if you increase the temperature, all these fine diamonds are washed out, so we cannot observe them anymore. However, this truncated diamond becomes a more clear diamond in this space at high temperature. And this means that we are actually able to see at mid-temperature range that one electron can be stably trapped in this zone without contributing to current. So it's already a big achievement, but we were curious if we really are dealing with a molecule formed by a few donors. In that case, we should have deeper charge states. If we raise the temperature further to 150 Kelvin, we indeed observed two more Coulomb diamonds at deeper charge states. And that means two more electrons can be finally observed by raising the temperature. And the third electron is also barely seen. So midway to room temperature at 150 Kelvin, we can actually read the operation of this device in the following way. As we increase the gate voltage from, let's say, 0.2, 0.3, up to 0.4, exactly one electron can be added into the channel. And if you switch the voltage a little further, you can get even further addition. Is it okay? Everything is fine?
நெத்தி வலிக்குதா ஏன் வந்து படுத்து விட்ட தலைவணி என்ன வச்சிருக்கிற
Please mute the mic, participants.
Is it okay?
Please, participants, mute the mic.
இந்த தலைவணி வச்சிக்கிறியா
Sir, Rajesh sir, can you please
என்ன
mute
செய்யுது
all
போன் அடிச்சா எடுக்க
Madam, you are set to black it, madam.
சார்ஜ் இல்லையா
Sir, audio
சார்ஜ்
settings.
இல்ல
You are set to black it.
Ma'am, I'm checking, ma'am.
Unmute yourself, madam.
Okay.
Better.
Sorry, sir.
No problem, no problem. But
Yes.
I can
One
continue
of the
later.
participants
But it
has,
may
என்னம்மா வாங்கணும்
Who is
Unmute,
speaking?
madam. You go to setting to unmute everyone.
It's okay. Okay. So sorry for the delay.
என்ன
So
கை வாங்கணும்
should I continue?
Yes, sir, please.
Yes.
Please.
So basically, we were reading this device as it's shown here, and this is, in a way, a very elegant controllability of single electrons. We need a few hundred millivolts to change the charge state of quantum dots. So it's not a
phone
very
மாத்திட்டேன்
difficult challenge.
phone மாத்திட்டேன்
Unfortunately, as we increase the
college கிட்ட
temperature,
Just a
college
minute.
கிட்ட
Just a
yeah,
minute,
I
sir.
will wait a little
Just
bit.
a
Okay?
minute.
college கிட்ட
Sure.
Just a minute. I'm sorry. Can any one of the administrators check and mute the participants?
phone
Okay, so maybe now we are all back to normal. Can you
Please
hear me now?
continue, sir.
Thank you. So unfortunately, at 200 Kelvin, as I mentioned, as we approach room temperature, these are all washed out, so we cannot observe these structures anymore. And we only see the zero electron case, and probably some signatures are.
Sir, you are muted, sir.
Okay, now it's fine?
Yes.
Yes, sir.
Okay,
Yes, sir.
thank you very much. So, well, what I've shown earlier was that this is everything is washed out at 200 Kelvin. In this IDVG characteristics, you can again see this very prominent current peak at 100 Kelvin. The blue line corresponds to 150 Kelvin. We can still see dominant current peaks, but as we increase the temperature, we are better.
So you're muted again.
Yes, I don't know why this happens, but
Okay.
Okay, can you hear me now?
No, yes, sir. Yes.
Okay. So hopefully it stays unmuted. So we are actually observing only a few weak inflections in the structures of FET behavior. So let me just move to the next slide. Okay, so why does this happen actually? It's the reason for this is that the barrier heights are very high now. So we observe actually from an Arrhenius plot analysis, we can observe that there's oscillating currents. So let me confirm that you can hear me now, right? I can be heard properly. Okay, maybe so. So from an Arrhenius plot analysis, we can extract the barrier height. The effective barrier height is actually relatively large, 150 millielectron volts, and that is significantly larger than the KBT at room temperature, than the barrier height of a single dopant. So everything is fine. These oscillations are due to so-called Coulomb blockade of activated conduction. So I will skip that explanation because of for time's sake. But please understand that even these oscillations from the expected barrier height have a meaning related to the single electron tunneling currents. So I will leave you with this message that in this applied physics letters from 2017, together with Professor Samantha, we actually provide a very important overview that we can bring this operation to midway towards room temperature. Now, I will skip this because this is already included into the structure into the paper that I mentioned. How can we further increase the operation temperature of these devices? So this is another work from one of my PhD students, a different one, starting from the concept of junctionless transistor. Maybe you are very familiar with this. This is a transistor which does not need the NP or PN junctions. It's actually uniformly doped at relatively high concentrations, 10 to 19, 10 to 20 per cubic centimeters, but at the same time, it is very, very small. So we tried to do the similar thing by creating a nanowire in a SOI wafer, doping very highly, but actually squeezing the sizes to become, in terms of thickness and width, less than 10 nanometers. If you do that and you tune the doping concentration, which is this horizontal axis, you can leverage the fact that the interdopant average distance, which is plotted from a simple calculation on this vertical axis, can actually become very, very small. So, for instance, if you choose a 10 to the power 20 per cubic centimeters doping concentration, the coupling or the distance between two dopants becomes on the order of 2 nanometers, just the Bohr radius. So we will have automatically formed molecules in our devices. We have an opposite problem now. The dopants are so closely packed that actually there is a metallic conduction between the source and drain. So the purpose of this work was actually to demonstrate that dimensionality is very important. It is metallic until we are building it into nanowires, which breaks down the uniformity of a dopant distribution. So I'm showing here only the champion data from our devices, which was obtained for a device with a width of about 15 nanometers and the length of a channel of about 20 nanometers. And I'm showing here drain current versus gate voltage at different low temperatures first. You can see that there is broader current peaks and very fine current peaks superimposed on each other. Well, the reason for this is that we are dealing with two different quantum dots working in parallel. But what is the most important is what happens at high temperatures. Even at 300 Kelvin, we can still observe very prominent current peaks, which are actually illustration of survival of SET operation even at these high temperatures. So as reported in this Applied Physics Express paper by my PhD student, the analysis leads to the fact that we are dealing with two quantum dots in the channel. One is a little bit smaller, one is a little bit larger. The sizes can be calculated from the periodicity between these peaks. And in a way, we were able to observe SET through these two different quantum dots, but suppressing, cutting off these metallic paths between source and drain because we squeezed down the dimensionality of the channel. So this is room temperature operation of SETs, and this is what I wanted to leave you with about this part of my talk. So if time still allows me for a few, maybe a few more minutes, everything is fine. I'd like to talk about silicon nanodiodes. So please tell me if I'm going over time too much. I will stop at any time. So
yes, sir, you can proceed, sir.
Thank you very much. So silicon nanodiodes are also another very important electronic device, not only transistors. And they exhibit in our research atomic level functionalities and maybe also importantly, single charge band-to-band tunneling. So I'll show you what kind of device we use. They are the so-called Esaki diodes, which were proposed by Leo Esaki a long time ago, and which have the operation very unique. They are not rectifying devices, or they are rectifying in a different way. The reverse current is actually very high because we are seeing band-to-band tunneling, such as similar to Zener tunneling. In the forward bias, we can observe a NDC peak, negative differential conductance peak, due to the fact that we are having degenerately doped P and N regions on both sides. Electrons are plenty in the N region, and states for electrons to tunnel in are plenty in the p-type region. At the same time, depletion layer is very narrow. So quantum tunneling allows you to flow currents actually from right to left in this view. The middle part is excess current, and the upper part is the regular thermally activated current of a PN diode. Not very important at this story, but the focus is around here, which allows us to see band-to-band tunneling at this low forward bias. Also reverse is very interesting. So we tried to utilize this kind of, propose this kind of new mechanism as a new option. But for that, we also needed to fabricate the devices in our lab. So I'm returning back to this schematic because this is a silicon-only insulator wafer, and we doped this laterally, which is quite unique and different from the typical way to make PN diodes in material science. You make it vertically. We actually dope the left side as a p-type, and at that time we use we use different masks. So when we dope the p side on the left, we cover the right side with silicon nitride layer as a mask. When we dope n-type on the right, we cover the left side with silicon dioxide as a mask. And these are all done by electron beam lithography. So this is a AFM image of a PN diode. Some non-uniformity in thickness and width is observed, but we can also identify this way where the junction is. Our struggle was to raise the doping concentrations to the order of 10 to the power 20 or higher for both P and N, which is doable in phosphorus. It's not so easy to do in other materials, doable in silicon. So this way, we obtain the degenerately doped N and P regions, and we can expect that the depletion layer width is narrow enough to allow band-to-band tunneling. So with this said, I think now we can expect that there are some effects due to thin SOI layers. Dielectric confinement will play a role, and I will explain a little bit about our applied physics letters from 2016. And at the same time, because we have many dopants in these depletion layers, clusters can be expected, and that was the core concept of this other APL paper. So first of all, what would happen if you have phosphorus and boron coupled together in a depletion layer? Basically, they are known as shallow dopants because the energy levels are only 45 millielectron volts near to the respective bands. However, if you make it very thin, two-dimensional, even one-dimensional, the levels are deepened, and then the phosphorus and boron can actually become pretty close to the mid-gap. In that way, phosphorus and boron, either single dopant or clusters of dopants, can introduce gap states. And these gap states become, surprisingly, stepping stones on the way of an electron from, let's say, N plus lead towards the P plus available states. So this mediation of the dopant states is actually very important for fundamental applications of dopants. What we observed in our devices, in a very peculiar device, is the similar characteristics to an Esaki diode, high reverse current, reverse bias current, and also NDC peak in the forward bias regime, but also a very sharply enhanced current peak. Now, this sharply enhanced current peak is illustrated here as a function of VP, bias applied to the P side, and also V sub. We can use the substrate voltage as a gate. So we can actually monitor what happens if you align two such energy levels, one induced by a phosphorus quantum dot and one by a boron quantum dot in sort of resonance. If you apply different VP, then we move them off resonance, but we can recover the resonance by applying substrate voltage, which is differently coupled to each of the dopant states. So with this, we have a proof of principle of the fact that gate control is observed, and this was submitted to and published in Applied Physics Letters together with Professor Michiharu Tabe. Now, that was not enough for us, and we wanted to understand the physics more, and we appealed to ab initio simulations where we mimicked our nanowires as p-type, n-type wires with exactly one phosphorus and boron on each side and compared them to the non-doped case. And under the right conditions, we can observe indeed this kind of sharply enhanced current peak, which only belongs to the case of when a phosphorus and the boron dopant mediate transport from one side to the other. Now, what this means is actually that we are looking here at an atomic level p-n tunnel diode. And that brings me to the fundamental functionalities that I was mentioning earlier. We still investigate how the energy states are created, if a single dopant is responsible or a cluster of dopant. This is another issue to study. Hopefully, we can cross paths in this kind of study in the future. Now, one more concept was actually developed together with another PhD student from my lab, who incidentally comes from SRM University. He did his master course there and then joined my group, Mr. Gaurang Prabhudesai. So he changed the perspective of how we see depletion layers actually for nanoscale. We doped very highly phosphorus and boron, and we expected indeed the depletion layer width to be very narrow. But our view of a p-n diode of a depletion layer is actually incomplete until we think about it atomistically. So we always have a gallium-like model image of doping concentrations and the macroscopic view of Venn diagrams, but the truth is shown in this view. Dopants are randomly distributed, boron on the left, phosphorus on the right, and both of them mixed at the junction point. So if the dimensions of the device is very small, then this mixture creates random structures. And if you take a scan through any of these points, you may observe a regular p-n diode Venn diagram in some points, like a conventional tunnel diode, but in other points, you could observe actually quantum dots embedded into this Venn diagram and modulating very significantly the Venn diagram. So this kind of view arises from the random distribution of dopants in this kind of low-dimensional diodes. So he measured many, many devices, and some of them were behaving as a regular Esaki diodes. This is a black curve. Half of the devices behaved like that. Half of the devices, however, behaved with a different peculiar behavior. They showed very low current at low bias and then step-like structure of a current. And that is also similar to a sort of staircase. Now, we understood that this could arise from the presence of a dopant cluster working as a single electron tunneling in a single electron tunneling mode, but we needed to demonstrate this kind of operation. So we measured the effect of V sub, and although the noise is quite high, we could observe actually in this kind of stability diagram, half of it only for positive VP, we could observe the modulations of current as shown here. And these modulations can be actually mimicked by a single electron tunneling circuit. I explained it a little bit earlier. If we tune the parameters to be consistent with what we expect in the experiment, we can actually simulate at the same temperature similar structures in our equivalent circuit. So that is already some proof. And if you take a line scan here, the experimental data and the simulation data can be made to fit reasonably well, with a few exceptions in a few parts of the device. But for us, that was sufficient evidence that we are dealing with a quantum dot. But looking at this distribution of dopants, it's still hard to say that we have a single quantum dot formed here. So we applied a new concept, a donor-acceptor compensation concept. Since we have many phosphorus and many borons, and they have opposite potential wells, they actually cancel each other if they are near to each other, at least nearer than Bohr radius. So if they are distant from each other, neighboring donors, neighboring dopants, so one donor and one acceptor, they can be still treated as isolated, and they influence the potential significantly by themselves. But if you remove the dopants which are compensating each other, the picture is much simplified. And now we can see these clusters arranged in a few places. Because we have larger donor concentration, we also have actually donor clusters more visible present in this depletion layer. So we counted statistically 100 cases. This is a little bit complicated statistics. The number of phosphorus donors is actually 2,000 in this nanoscale depletion layer. But then we can actually compensate, and after compensation, we are left with just about 100, 150 donors which matter. So these donors are now redistributed randomly, and we are actually monitoring the type of molecules that they form. So you can see here how many donors are embedded into each of these molecules. Based on the fraction of cases, this histogram shows that 5 to 10 donors could be a reasonably good quantum dot that can actually operate in the following way. It's a stepping stone for the electrons starting from the N lead, moving towards the P lead for band-to-band tunneling, while this is filtered to the level of single electron tunneling. So we can also understand the positions of the dopants and the extension of this quantum dot statistically. There is a lot of understanding from this paper, Applied Physics Letters from 2019. So I strongly encourage you to look into this if you want to change your perspective about how actually dopants and the randomness of a doping influences the devices. So probably just for 5 minutes more, I'll end up with what we can do with these devices for photonics. This is a work that we carried out in a simple way. We tried to take this kind of transistors, mainly the transistors, and irradiate light on top of a channel for devices which do not have a top gate. So if we are at a low doping concentration, we could demonstrate by picking up this kind of current peaks and irradiating photons in the visible range, we could demonstrate that although in dark current doesn't change, under light current does change by RTS. And actually it's a two-level RTS, and as I mentioned before, this means that we are sensing photons converting into electrons, trapped and then released from dopant states. Now, at the similar concentrations, low concentrations, but in p-n diodes, with both concentrations in the order of 10 to the power 18 per cubic centimeters, we should think very clearly about the atomistic distribution of the dopants again. Boron and phosphorus dopants can actually modulate the potential very dramatically. Now, if you irradiate light on these devices, we can see a different type of random telegraph signals. They are multi-level signals. In fact, if you look at some of the digitized RTS, it's a three-level signal with a low, medium, and high level quite clearly visible. This Applied Physics Express paper actually explains how this is related to trapping in a phosphorus and trapping in a boron atom almost simultaneously. So this is why we are seeing multiple level RTS. More recently, we looked at the co-doped transistors, which are very highly doped. And this work is done actually again with IIT Roorkee colleagues. It's very important for us to understand that co-doping is a new type, can build a new type of materials. If you are co-doping at low concentrations, ND and NA, we can create atomic functionalities. If you dope in the middle range, you can create molecules. If you dope at high concentrations, close to solid solubility limit, you can create domains even, or areas which are either N-type or P-type. And if you dope in an equal concentration, you can compensate almost perfectly, but please be aware that it's never fully compensated on the nanoscale. So we build this kind of transistors with doping concentrations illustrated here, and then we hoped that by irradiating light here, electrons and holes can be captured both in donor states and in acceptor states simultaneously. This could enhance the sensitivity for carrier trapping in our devices. So together with researchers from IIT Roorkee visiting my lab actually for several months, we studied co-doped SOI-FETs like this, with these parameters shown here, but with the top gate removed. What we have between source and drain is an extremely tiny channel, which is just a few tens of nanometers in width and length, and it looks like that. And we expect that this contains several quantum dots that allow you to power it into the single electron tunneling mode at low temperatures at least. So we do expect that these multiple SET paths allow us to observe a sensitive detection to photo-generated charges. So now we removed the gate. We looked at a device without gate and measured at low temperature the stability diagrams. As by now you are familiar, I guess, you can see the Coulomb diamonds a little bit opened and a little bit noisy indeed, where we can count actually how many electrons we injected into the system from a backgate voltage this time. So if you take the ID VBG characteristics, you can see the current peaks. And these are, again, telltale signatures that of the fact that this is a circuit that could work for our devices as well. So then let me show what we have under light. First of all, a visible light. And this is how we operated it. It's actually a very simple setup. We put our samples inside this metallic chamber under vacuum at low temperature, but we also irradiate light through this support system and through an optical fiber and shed it on the sample with the probes connected to the appropriate pads of aluminium. So a halogen lamp is used, but actually a monochromator cuts off the specific wavelengths, and that allows us to focus on specific energies of the photons. First of all, if you look at visible light, 750 nanometers, please note that this is much larger than the band gap of silicon. So in this case, we can easily generate electron-hole pairs from valence band to conduction band once the photon is absorbed. So that is very important. How our device is operated is analyzed in this complex slide. Actually, we measured many times, and we measured in different ranges. Current peaks can be clearly observed, and these are for different source-driven biases. And also, stability diagrams with Coulomb diamonds of different shapes can be also observed. Now, this analysis was very difficult because we had to follow very carefully, or as carefully as possible, different Coulomb diamonds and assign them to just a few donors present in the channel. And actually, you can see them here counted from D1 to D5, and actually we've repeated charge states later. So it's very important for us to understand that transport occurs through different phosphorus donors, and each of them can be actually a path of current. Now, also, it's very important to understand that a second electron can be added into each quantum dot because we are having deeper states. So now, in dark, we observed this kind of IV characteristics. Under light, however, with very low incidence of photons, we start to observe noise and also a shift of these IV characteristics. Actually, for better understanding, let me actually elongate or stretch this kind of characteristics. And now you can see a better match between the dark and the light characteristics. So what happens that changes this VBG effective scale is the fact that most of the photons coming from left side pass through the oxide, pass through the silicon layer, and they pass through the box layer, and they get absorbed mostly in the substrate. So this modifies the backgate voltage effectively. This is an important effect. More importantly, however, is what happens when we change the photon flux. And what happens is that the number of the changes of a current, of a so-called RTS, is also changing significantly. So if in dark we see practically no change, under light we see RTS, and it depends on the photon flux. And that's a signature that we are sensing our photons absorbed here. So to analyze this kind of RTS, it's very complex, and it's a field of study in itself. In this paper, they reported a variety of types of noise signals and how we can convert them through this WTLP, weighted time lag plot, into more meaningful signals. I will not get into the details. I recommend this paper, but we applied it for our devices. The place where we applied it most was to demonstrate infrared detectors. So infrared detectors are different than visible light. The wavelength is below the band gap of silicon. So in that case, silicon was not a very good detector for infrared light because it is transparent mostly. So other materials were demonstrated until now in a variety of architectures and structures. However, we are now showing that silicon can actually be used for this using the similar setup, but now irradiating with infrared light. And in that case, we are dealing with wavelengths smaller than the band gap, and something happens. And I will show you what's going on. So if you irradiate with 1780 nanometers, you can still see, compared to dark, 2-level or a little bit triple level RTS in our devices. as the flux is actually increased. Even if we irradiate with 1154 nanometers, we can still see this multiple level RTS, and now we can compare it with other structures. And in this case, this is the wavelength effect, and on the right is the photon flux effect. So we finally understood that we can actually detect photons not only in the visible range, but also in near and far infrared regimes, and that demonstrates, as shown in this paper, ultra-sensitive shortwave infrared single photon detection. Unfortunately, I leave the ultra-sensitive part for you to discover while you are reading this paper published very recently in Advanced Electronic Materials of Wiley. So this is a work carried out mostly by Ms. Pooja Sudha, who graduated now her PhD. And the bottom line is this: we have a nanochannel co-doped with phosphorus and donors. The situation is very complex in these channels, but the electrons can actually travel through a few clusters, and the light can actually generate carriers nearby in some traps, affecting, modulating this transport through the quantum dots. So we should understand that co-doped nanotransistors, because of compensation, because of randomness of a distribution, can create clusters of dopants. At the same time, visible light is very useful. We can detect it very easily, but it is not very elegant in a way. On the other hand, we can use the random telegraph signal analysis with WTLP, and finally, we demonstrated that infrared sub-band gap irradiation of phosphorus can actually be detected. And the reason for this is that the clusters introduce very deep states, and those bent tail states actually mediate the electron and hole capture effects. So what I'm trying to demonstrate here is that co-doped nanoscale silicon transistors can be a good platform for single photon detection, and hopefully we can explore this in the future a little bit more. So I took probably a little bit more than I should for the time, but I'm going to leave you with the following summary. Single donor atoms are indeed a versatile system for creating atomic level functionalities, but we have to stick to low temperatures. Raising the temperature is really challenging. Selectively doped multiple donor quantum dots can work for room temperature SCTs. We demonstrated that, and they are more robust, but they are not atomic level functions. We have to discard that concept. We can probe, we can interpret them at low temperatures. I've shown you a few examples, and even in Esaki diodes, in highly doped tunnel diodes, band-to-band tunneling current can be enhanced by phosphorus-boron pair, or it can be modulated by single charge tunneling. And these are new mechanisms that can all be leveraged for the next generation of electronics. I left you at the end with a bit of a flavor of photonics. Single photon detection can be achieved in various structures indeed, and that makes it a very good atomic and molecular level electronics platform for you to consider in the future. So this is a list of many collaborators, including many people from India generally, and more specifically from IIT Roorkee. And this is the end of my talk. I leave you with a few books showing that this is actually not a very theoretical approach to deal with single atom nanoelectronics. There are now books that are dealing with this kind of issues, and even we have a few chapters introduced there. So I leave you actually with maybe that was the last part. Sorry for that. So that was the last slide. Thank you very much for your attention, and I look forward to any questions.
Thank you, sir. Thank you for your in-depth and enlightening presentation. We'll have some questions from the participants. So the query from the participant are, what could be the challenges of ultra-high doping concentrations in nano devices?
So ultra-high doping concentration in nano devices can create several side issues. Maybe I'll just go to one of the slides. So the main issue is that it actually disturbs the lattice of a silicon. So we assume that doping occurs very naturally as substitutional doping. But when we do ultra-high doping concentration, interstitials will also play a significant role in the doping. And those interstitials create stress, strain, and they may modify the properties of silicon itself significantly. So we have to deal with concentrations that are sufficient for us to create quantum dots without disturbing the lattice of the silicon too much. So this is maybe the most important challenge.
Okay, sir. Thank you, sir. Sir, on reducing the silicon nanowire thickness less than 10 nanometer, will it affect the device performance, sir?
Less than how many nanometers? Sorry for that.
10 nanometers.
Okay, so of course, but this can be perceived as a positive effect. So if you reduce less than 10 nanometers quantum confinement, and if your device is embedded in an insulator, dielectric confinement will also play a key role. So if you do that, the dopant states will become deepened and probably randomly deepened, and we cannot treat the dopants as a classical textbook dopants anymore. And of course, the surface effects, interface effects will be very important. So annealing can be one solution, or control, very precise control of dopants with some sophisticated techniques can be another one. STM manipulation is demonstrated in Australia, by the way, and we can hope for that kind of more practical application.
Yes, sir. Thank you, sir. So the last question, sir. In what way do SOI FETs benefit from using highly doped nanowires?
So, sorry, can you repeat a little bit?
SOI FETs benefits from using highly doped nanowires.
Okay, so SOI FETs are the ones that we are actually hoping to use in the future generations of the electronics as well. But our perspective is a little bit different. The classical mechanisms of operations are actually affected detrimentally by the doping. Randomness of the dopants is actually shifting the threshold voltage significantly from device to device. So this uncontrollability is unwanted for the FET in the industry. On the other hand, this kind of fluctuations allow us to put to work the dopants themselves as the active parts of a device. So we are trying to change the perspective and move away from the CMOS compatibility, CMOS type of devices to, let's say, single electron dopant-based devices. And in that sense, well, it's a new type of device. Okay, and for FETs, it's kind of detrimental.
Yes, sir. So one question, any open source software is for quantum computing?
Yes, of course, this kind of system is very easily converted to quantum computation, and therefore it's a very reasonable question. There are, to my knowledge, I think NanoHub, for instance, is a very good platform where you can find a lot of open source software applications, lectures even, and it's controlled from, I think, from US university. And so NanoHub is my recommendation for finding information.
Okay, thank you. Thank you very much, sir. Thank you very much for such an excellent and highly informative session. It was truly insightful and has greatly enriched our knowledge in the field of nano device technology. So we sincerely thank you, sir, for your time and effort you have taken to share your expertise with us today. On behalf of all the participants of this ATAL program, we extend our heartfelt gratitude for your valuable contribution, and we look forward to more such interactions in the future, sir, at SRF.
Thank you very much.
Thank you very much. Thank you very much, sir. I am Professor Aruna Priya. I would like to also thank Professor Hiroshi Inokawa for introducing you to us. Yes. And on behalf of the entire team, we are very thankful and grateful to you. Hope to meet you in SRM in the coming days.
Sure. So October, November, I will be there. So looking forward to meet many people and continue our conversation. Thank you very much for the invitation.
Thank you, sir.
Thank you.
Goodbye.
Bye. Shall we move on to the next session?
Yes, ma'am.
Sarin, sir, have you joined, sir?
Yeah, I'm here.
Yes, sir.
That
Yes,
was
sir.
an
Good
excellent
evening,
session. But do you want to give a break for 5 minutes to people, or I'm
No,
okay
sir, we
because
will
that was a long
continue.
session.
No, sir. People would like to have a little earlier also. So let us start continuously. If we give a break, rejoining is an.
Sure.
So
Please
we'll
let me know
continue.
if you can see my screen.
So now, shall we start, madam? Next session?
Yes, sir. Yes, just a minute, sir. We'll give you a formal invitation and then we will start.
Yes, ma'am.
Yes, ma'am.
Now let us move on to the next interesting session titled Defects, Process and Pursuit of Perfection by Professor Sarin Sundar. It's my privilege to introduce Professor Sarin Sundar, a highly accomplished expert in materials engineering with a distinguished career spanning nearly 3 decades. His journey reflects rich experience in advanced industrial and institutional R&D, technology management, and innovation leadership across India, Europe, and the USA. He has held prominent roles such as staff process engineer at Applied Materials and scientist at ARCA and MTAB, and since January 2024, he has been serviced as Professor of Practice in our SRM IST. His expertise spans R&D management, unit process, and high volume equipment development, technology programs, and risk management and statistical DOE. Sir has made significant contributions to semiconductor deposition technologies, thin film and solar manufacturing, lithium metal anodes, and solid-state batteries. And he also been instrumental in new product development from conception to high-value manufacturing and holds several US patents with impactful publications. He has advanced laser-based material processing for aerospace and automotive applications and collaborated widely with Fraunhofer institutes, universities, and national labs in California and Germany, strengthening global research industry networks. Currently, he is working with research faculty to bring the latest technology in quantum technologies, semiconductor technologies, and industry academia collaborations. Please join me in warmly welcoming Professor Sarin Sundar sir, a technologist, innovator, and inspiring leader in material engineering. I invite you, sir. Please take over the session, sir.
Yeah, thank you, ma'am, for the kind introduction. And I hope I am audible. Is it loud and clear?
Yes, sir. Yes, sir.
And can the participants also see my screen?
Yes, sir.
Yeah, thank you. So I don't want to come between your dinner, and I'll keep it as short as possible, but still I hope I'll do justice to the topic. I saw the agenda and this for the ATAL 6-day FDP program, and I thought I would cover more from the materials engineering and also normally topics which are not covered and which are more relevant. And this presentation will be slightly different because I'm mostly from an industry. So industry, we can't share results and say microstructures and graphs that we have worked on. Even I'm out of applied recently, but still we have a 5-year non-disclosure on things that we have worked on. But then what presentation I showed you will be predominantly from applied relevant to this topic, and also this will be external use material which are publicly also available. I can also send you the link, and the presentation also will be shared after the session. Yeah. So my topic, I just try to group them into 5 categories. One is want to give a short introduction about semiconductor manufacturing as from the industry perspective, and also where we are going to go in the next 10 years and what are the typical processes and defects. That itself is a huge subject, so I'll be able to give an overview, I hope, and also some of the process control and defect review equipment used in the industry and what is the latest, and I'll give some examples from applied material, and also a takeaway slide what the faculties and students taking this FDP probably should look at after this course. So this is a quick overview about my career. Probably you have seen I'm also currently Chief Technology Officer of a industry nearby, and primarily I am associated with as a professor of practice at SRM, the Department of Nanotechnology and Physics, and I also work with other departments here, and also with the other institutions also. So let's straight away move into emerging technologies. And please do ask your questions in the chat box. And if I'm not able to answer, I'll definitely reply to you by email later. And so most of you have seen this. This is a typical semiconductor ecosystem. So you can also go to the Stanford Guardian Node Center and download the latest version. So basically, you know why you're all here, but still, I'll just give a quick overview. On the pyramid, on the triangle you see on the right, this kind of summarizes various kind of companies that forms ecosystem, and this constantly changes. So once upon a time, on the topmost three, these are primarily the fab and fabless companies and the foundries. These are the guys who primarily makes the chips. So once upon a time, even IBM and AMD had their own big factories. Now they don't. So they're all become fabless companies. And on below that is there are many companies. These are called the wafer fab equipment suppliers. So I was working in Applied Materials, which is part of one of the biggest wafer fab equipment supplier over the last 55 years in the history of semiconductors. And I hope some of you also have looked at the overall application ecosystem. And I hope most of you are from India, and you know that most of the semiconductor manufacturing, which I'll be focusing on, has applications across biotech, AML, and quantum computing, and also the semiconductor ecosystem supports all these areas. And the ecosystem in India, I think today we have an excellent industry institution interaction session where we have Professor Rao Tumala and also Mr. Raja Manikam was here in SRM. And we already have announcement of about 10 big semiconductor factories in India and 4 more yet to be announced. I hope those 4 will be announced in 3 weeks during the Semicon. And again, this is a long time pending. The reason I'm showing the slides is that whenever a semiconductor fab, whether it is a logic fab or a memory or a ATMP or OSAT activity comes in, the whole ecosystem has to be created. Ecosystem meaning hundreds and thousands of supply chain companies, and there is a manpower requirement for that. So the India has made a semiconductor workforce development program. And today we had, in the morning, we saw some slides from Professor Ratumala on that. And on the right-hand side, you also put the semiconductor value chain here. There you can see the equipment companies here. And also you see the various the fabless companies and also design companies and the foundries. So, and also there's a small mark here in yellow that's in trillion of market value. So the market capitalization in trillions of dollars. These are all a huge market, and this is going to be there for the future. There's no future without semiconductors. And if you look at the overall distribution of semiconductors, it is dominated by logic and memory. Of course, you have a lot of other things, the discretes and the sensors and various displays and so on. But then it is primarily, in terms of value, it is still dominated, and it will still be that way because of the AI and push. So if you want to look at a little bit of history, so what has happened since probably the 1980s. So on the left-hand side axis, you see values in, say, billions of dollars. About 1 trillion is here. So the last 40 years, we have reached close to $466 billion in terms of market value. And we are today somewhere around 2025. And most of the forecast, this is an older slide, and most of the forecast says that whatever happened in the last 40 years in terms of the semiconductor industry manufacturing, that is going to happen in the next 5 years. So by 2030, we will be having almost that much earlier, and this will be predominantly pushed by AI and also various electric vehicle and other industries. And And these are all significant shifts in terms of trillions of dollars. If you see, almost $8 trillion worth of opportunity, and it is it already created data centers. You can see the list of data centers. US has thousands of data centers. India does not have that AI data centers, but we also look at the we know recently US they announced a Stargate. It is supposed to be the biggest AI data center in the world, and that's going to be a $8 trillion market by 20 in the next 5 years, and this will determine a huge shift in what we do. Which you already see. We see the chat GPTs and various AI programs and various being created to support that. And similarly, edge AI and IoT, so devices communicating. That's a $2 trillion by 2030, and also electric vehicle and autonomous vehicles. That is again the big. We all see that happening, and also energy with solar or wind. That is again a big one because. It goes hand in hand with all the other three. So if you look today with the overall energy consumption in the world, people don't realize that more than 10% of all the energy we produced are used only for computing. Your cell phones, tablets, laptops, and data centers, Bitcoin mining, and so on. And this is going to significantly change in the next 5 to 10 years. And I think in the US alone, they look at the one estimate is the recent sustainability report, which came out last week from Applied, says 20% of all the energy that is produced will be used only for computing. And all this again translates to how you design, how you manufacture, and where the defects are. So, and you also see the energy consumption on, say, driven by the training the AI models. I think now the GPT-5 is out 2 weeks ago, but you see it's from between 1 and 4 itself, there is a 10,000x increase in flops, so in floating point operations, and also the energy consumption is increased 250 times, and the AI accelerator chips are extremely hotter, and they require huge amount of power to do run them to train the model. And I'll just quickly skip through some of these slides because you know them. Only thing I'm showing this because it will lead me into the defects presentation later. And this is the old Apple A14, and which is typically about 10 millimeter square or 10 by 10 millimeter square, 100 mm square, and say inside, if you take a cross section, you will see the chip cross section, and then at the bottom of this is where your transistor lies. And this is A14 is 5 nanometer technology. The transistors are 11.8 billion, and these are like FinFET, but still 11.8 billion transistors in a single chip. And for that 11.8 billion, you need typically 24 billion contacts and about different types of threshold. You know all this, but then when we manufacture this in large scale, in a full wafer, there is going to be defects which will determine whether the chip will pass or fail, and that will determine the yield of the factory, and that will determine whether the technology is successful or not. In fact, there's a classic case happened last year when I gave this presentation. We did discuss about Intel, and you know what happened to Intel last year, and today the US government is investing in Intel, TSMC is investing in Intel, and then and it's all because of the yield with the 1.4 nanometer technology, but then there is also the future roadmap and how the demand taken by the AI programs. So we also see here another slide where we talk about the interconnects, right? So this particular picture, same picture from the last slide, but we really focus on the back end of line interconnects, and there you have about 15 layers of typically this for the A14, and today it can go up to 19 layers. And today there are also new design architectures where they are using backside power delivery, or the power delivery is taken on a separate chip and bonded together. And this has more than 24 billion contact trenches and via connection. So as you see, there is a lot of patterning requirements, and patterning requirements, especially the lithography, that it is one of the primary source of defects also. The reason being, each lithography step, each patterning step, you know, you need to put a photo mask, and the mask usually is very thick. So even if you talk about nanometers of structures, the mask is still, the smallest mask is still 0.5 micron. So 500 nanometers is the smallest, say, photo mask thickness. And in addition to that, you need to have multiple anti-reflection layers on the top and bottom. So we will, and then you, after patterning, you have to remove it. You have to strip it, ash it, or then chemically clean, clean it with water. Then it may leave some particles there, and the particles are huge. So one particle in one layer of the process, and for multiple processes, it will add up and cause huge issues. And so you need inspection. And similarly, here you see DRAM. Say DRAM chip. So here this is a DRAM chip, and there the architecture is different, and we have similar problems both with processing and also with defects. And now here you can see this is on the 3D NAND. So 3D NAND, typically in the market you buy your SSDs and say pen drives with SSD memory, NAND memory, three architectures. And today you can get up to probably more than 236 layers. And as we speak, I think today there are also work going on for 1,000 layers. So it has an extremely large, say, high aspect ratio holes to be etched. And again, very, very sensitive to defects, because even in one layer of the 1,000 layers or 256 layers, you have defect that will translate into the performance of the whole stack, right? And this is an example which I showed last year also. So for example, the NVIDIA Meta's Llama 3, which is in your WhatsApp, you have an AI. This was trained last year. The training typically takes about 3 months. And this was trained using H100 NVIDIA GPU. And almost one chip failed every 3 hours of the 16,384 GPU cluster. And if you see the training cost is also increasing. In fact, this is again from last year, but this year it is even more than 250, almost close to $500 million this today for training a model. But this again justifies a need for tighter control on defects in manufacturing. And not only today's manufacturing, if you also look at the roadmap, this is a roadmap from last year from IMEC. So most of you know how to interpret this. The N is nanometers and A is angstroms. So today we are somewhere here. So 2 nanometers and also 1.4, 1.8. So the people have been working on this right now. And there is also more challenges when it comes to this is the process technology node. This is not actually, we will come to that when in another slide, what it actually means. The actual metal pitch here is somewhere between 21 nanometers, right? And the gate will be about 48 nanometers even for a 2 nanometer technology node. You can look at IRDS documents. One moment. Am I audible? Am I talking too fast, ma'am? Are people able to follow me?
We can able to follow.
Okay. So if you want me to talk slow, then please tell me. Okay. And also another challenge with when it comes to both defects and also processes or like all architectures are becoming three-dimensional, whether it is logic or memory or also even advanced packaging, because most of the AI accelerators have HBM memories where HBM chips are stacked one above top, on top of each other, and it's becoming more complex. And also, as I said, the AI accelerator chips. If you want to have a quick and fair comparison, so the logic processor in your cell phone typically take 10 watts of power. That's a design a TDP. And whereas the processor in your laptop or a desktop is typically around 65 watts to 135 watts. Whereas the AI accelerators today, what is the NVIDIA Blackwells, these are almost in kilowatts. It's about 1.2 kilowatts. Even the B200 is slightly optimized within the Blackwell H200. H100 is about more than 1,200 or 1,400 watts as a TDP. That's a huge amount of heat generated. And in fact, last year we had a classic example with the HBMs. Also, as you have seen in the other slide, the HBMs fail because they have like memory loss. These chips, memory chips fail if the temperature goes above 95 degrees, the operating temperature. So when you stack them up, normally somewhere in the middle, it goes more than 100 degrees. So whatever is stored is lost. So again, people are now moving back to DRAM, but that question is still there. But again, companies like NVIDIA, Micron and SK Hynix, they are working on it. And also, if you see on the logic side, I will show you a short video of gate-all-around, mainly to show different kinds of processes, both the manufacturing processes and also the defect inspection processes that we do. And before we go there, probably you can look at the number of steps. Steps here is the number of manufacturing process steps. Usually your CVD deposition step, or your material removal etch step, or your material modification step, or your inspection step. The 28 nanometer node typically had about 750 process steps. Today, we have more than 2,100 process steps for the 2 nanometer gate-all-around. That what you see on your right-hand side is a typically silicon nanosheet, and in that only the front end of line, only on the front, the gate-all-around formation. In that region alone, you have more than 500 steps. So and any single defect there can entirely have a huge yield problem. And also, if you look at between the 2 nanosheets on a typical gate-all-around transistor, so between here and here on this picture on the right, the typical thickness is about only 10 nanometers. And in this 10 nanometers, there are 5 different materials. This need to be deposited and also removed in a very precise fashion, and also inspected for defects. Right? And then this is all already there. It's already going, and this has to be done repeatedly across 10 trillion transistors on a single wafer. So we talked, and that's a huge amount of inspection requirement. And this is done usually by SEM, scanning electron microscope, but then this is not the one that you use in university. So this is non-destructive. You have to directly see. And also on the back end of line, on the interconnects, you can typically use optical inspection. And also, this is also only going to increase, because we saw the gate-all-around. What we saw is a normal transistors, and if you look at the advanced AI requirement, you see on the right-hand side, you can see various artificial intelligence accelerators developed by various companies and their first date of introduction. And for example, Google has their TPU. The TPU today it's in generation 7, Ironwood, which was announced in April. And the reason is all the AI push for what is happening now requires huge performance improvement. So when you say performance, when you look at Moore's law, the classic 2D scaling, you can have only a performance gain of 2 times. Whereas when you change the architecture, you can have up to 2,500 times performance. So that's why these chips are entirely different. And on the other side, on the left-hand side, you have again our old slide from what we have shown last year. This is showing various artificial intelligence model. This has been used around. So the oldest model is somewhere in 1962, Perceptron. And today, of course, you have the latest either Grok 3 or GPT-5. And there's an exponential process computing power that is required both for your training. That's why you require huge data centers. And between Moore's law performance gain and also from the AI push, that's why many companies say that Moore's law is dead in 2015, and some say it is still existing. And of course, it depends on our interpretation. And of course, we also talked about memory, whether it is HBM and DDR. So last 2 years, I said HBM is the order of the day. So also people wanted to do more on HBM. And we are also looking at RAMs, 3D DRAMs that will work 1,000 times faster than the current NAND. So there are roadmaps for this. So on the right-hand side, if you see a DRAM cell, a working memory, the write speed is about 10 nanoseconds compared to your current NAND cell, which is 50,000 nanoseconds. And the endurance is also much higher. And the work is going on this side also. And today, people also find that DRAM is more stable, doesn't fail. At least the memory loss problems are not there when you do that AI training compared to HBM. And here it's a small HBM process flow. So basically, I'll probably skip this and go into the defects part. You will see in the presentation. And yes, so this is also the HBM for FinFET, which is now the latest technology. And currently, earlier, 2 years back, it was mostly on the planar side. So 28 nanometers is still planar. So some of you, if you look at technology node wise. And now I'll start a little bit to overview about various processes and defects for the angstrom era. right? So now this is sub 2 nanometer era. So instead of 2 angstroms, now today we have 1.4, 1.8. So I will like to start with the video before that. It's a 6-minute video which will explain the gate-all-around transistor. So I hope I can show the video if it is working here. This is a video from Applied Materials. Please let me know if you cannot see, or I can show other ways. So can you see the video?
Yes, sir.
People can listen to the audio also?
Audio not coming, sir. Only video is coming.
No, right now it is stopped. When I play, it will come.
Okay, sir.
I'll put the captions also on, or I'll send the link later. So couple of things I want the participants to look at this video. One is the various kind of process steps. And in between the process steps, there will also be measurement steps, defect control and how they measure, what kind of equipment is used for that. But it'll be a little fast, but of course I will send the link of these videos. These are all available in YouTube.
You're not getting the audio, sir. Is it fine with the captions we are getting?
Okay, so what I will do is I will send this on the chat box so people can look at it later. But right now, for this program, they can probably look at the captions.
Okay, sir. Thank you, sir.
So I think that video is over. Can I continue?
Yes, sir.
Sir.
Okay, I think you saw how currently the gate all around process manufacturing process is being done, and as I showed you this slide before, you see almost 500 process steps. So typically, 750 process steps in 28 nanometer takes about 3 months to complete. So today, even with advanced machines, it may take about close to 8 weeks for only for the front end process fabrication here, and it's a lot for you can understand the complexity when we are going much closer in different kinds of materials and a lot of ALD processes, both atomic layer deposition and also atomic layer etching, and also the inspection that you saw. You can do a multiple 3 layers of nanosheets you can do in a single inspection. So we don't, you have to look at the kind of different methods have to be done. You have to look at the kind of residues. And I'll, before getting into more of the defect products, I will also want to quickly show about what you can do with simulation of the defects. So last year, I think an SRM and also many other institutions got the access to another industry software called Simulator 3D. In SRM IST, we have this year about 150 licenses between ECE department and also the nanotechnology department. You can do visual modeling and calibration of various defects. You can actually, without, if you don't have the equipment, like even a research fab like IISc Sense or IIT Bombay requires more than 1,500 crores to establish. But then you can do a virtual emulation using these softwares. In this particular slide, what you are seeing is a line edge ratio, especially after lithography. You can see the line edge roughness. And then sometimes you also get shorter lines. This actually you can model and quickly emulate in your software. It's now the LAM is given $400 million to Government of India to release across various universities, and various universities can actually apply for this program and get these softwares into your university, and you can directly talk to LAM or ISC and the India Semiconductor Mission regarding this. And coming back to defects, why defects matter? Because at this scale, what we are doing, defects are invisible. And this is the key drivers for yield and cost. I hope most of you know what yield is. And every defect is a killer defect. Right, and the industry has ways of overcoming it. That's what you're seeing on your right hand side, and at the scale at 2 nanometers and beyond, it not only it's mission critical, meaning it's just not killing the product, it can kill the whole company, right? So and if you look at the semiconductor manufacturing, many companies, even the biggest company like IBM, which is still a great company when it comes to semiconductor IPs, and they're still number one. And even they stopped all their factories because when long ago, about 10 years ago, and because when you upgrade to each technology node, the amount of investment in the fab is extremely large. So the yield is very important factor. And today we are also talking about advanced architecture where it is DTCO and STCO. This is basically device technology co-optimization and moving on to system technology co-optimization. So you heard a lot about systems today, including packaging. And these are the drivers why defects are very important. And here is a very short list of defects, and one of the major ones. The source of defects for probably in lithography is pattern collapse, overlay errors, and the lineage roughness, residues during etching. In deposition, it is thickness uniformity, non-uniformity, or voids, and the CMP you have scratches, and it the impact entirely worsens when you go for 3D architectures. And there is a separate document on IRDS. IRDS is the old ITRS, the roadmap, and the 2024 as the yield enhancement. Probably I'll also show you one picture from that. And if you understand difference in the market, if you go, you have processors like i3, i5, and i7 in Intel, and Ryzen 3, Ryzen 5, and Ryzen 7. So I hope some of you know what the difference is, and I don't know if it can be interactive in this session, but anyway, I'll just, you can also go and check in Wikipedia for probably about 10 years ago, or maybe more than 10 years, they brought this nomenclature. Basically, your i3, i5, and i7, or Ryzen 3 and 5, these are exactly the same chips. It's all coming from a single wafer. So when you have more defects, they have to disable the cores. So if it's a i3 is a 4-core, 6-core, or i7 is a 8-core, so they disable 2 cores, and the processor with more defects with less number of cores is i3. So it's the same mask, same process, but when they do a wafer mapping and find out the defects, then accordingly they have to classify, because they cannot throw away the chip, the defects. They have to make sure it still works. That's also you also see in the pricing. But all companies don't do that. If you see Apple for their M1, M2, M3, M4, fourth generation processors, they don't classify it like this, which is one of the reasons it is also more expensive to control the defects. They can't sell a processor with defects, right? I hope some of you get this. There are several videos on YouTube regarding this classification. You can look at them. And yes, this is about the IRDS. You will find also a classification of defects in IRDS and where it comes from. Right from the material in the crystal, stacking faults, contamination, stress, and also how the silicon wafer is prepared. That's why we never use silicon wafer as it is in the factories. You have to grow a epitaxial, highly pure silicon layer first, and then only start your device fabrication on top. And between the devices, you have kind of overlay errors. Between the interconnects, you have ESD damage, cracks sometimes, and also layer thickness, uniformity, contaminations, and also, as you have seen earlier, different processes can contribute. And you will also find many of these things listed in the litho roadmap document, again in NIRDS. And one important thing that I want you to see in this particular screen is people talk about 2 nanometer technology node, 1.4 nanometer, or in the particular case, it starts with 3 nanometer, the latest document, or 5 nanometer in this case. Those are process technology nodes. So the actual nomenclature is here is on the first row. It's a gate 48, metal 24. That's actually the new nomenclature that IRDS wants you to follow. I think some companies like IBM follow this, and all the other companies use their marketing term for the node 1.4. Say angstrom, some call it angstrom, some call it nanometer nodes. It's actually the process technology node. So the gate actually is 48 nanometers, and metal is about 24 in this particular 3 nanometer node. And also even how much defects are accepted, those kind of documents are already there. So I will quickly now share to another presentation where I will talk about, can you see the different presentation from me? Hello?
Yes, sir. Applied Materials Technologies.
Correct. So this here is where I'm going to talk more about the defects and also the equipment, actually from Applied Materials. You can also see this online. So basically now we have covered materials engineering, how to manufacture chip. Basically you can only four activities. You can group them into 4 activities. One is creation or deposition of different materials. So if you look at the periodic table, there are almost 40 elements and various combinations of them are used today. And primary being epitaxy, metal deposition, dielectric deposition, plating, there's copper plating, atomic layer deposition, and also selective deposition. And then you have material removal technologies. You shape them. Of course, you have to pattern them before shaping. And there are also different ways of patterning, just not lithography. You can also do imprinting. So primary removal and shaping is etching, CMP, which is planarization, and selective removal. Either it is selective ALD, selective etch, and there are a lot of selective removal processes, and also selective pattern shaping technologies. And material modification, you also have to modify these materials' properties at that level, whether it is few nanometers. You saw like 5 different materials between 10 nanometers. You have to get them the right properties for the electrical and also the performance what they're designed for. So normally it is done by implantation or thermal or using lasers and various other treatments. So material modification, and of course process control. So some of them are inline process control and some of them are inbuilt inside the chamber. It is live when it is processed itself, we can inspect. And there's a huge amount of data is being generated. So the most critical are being optical inspection. Optical inspection is still widely used for most of the defect review. So reviewing the defects, and electron beam EB metrology is one of the very big technique used in the industry, and also CDSEM. So CDSEM is basically the industry standard. It's like your Fevicol from Pidilite, but CDSEM is from the industry standards from Applied Materials for the last several decades. Any factory you go, you'll just use the word CDSEM. And then again, for the interconnection, heterogeneous integration, you also have different kind of equipment. But what I'm showing in this slide is just only from Applied Material. There are also other companies which makes them. Here it's a much larger sheet. Again, depending upon the equipment, whether it is 150, 8-inch, or a 12-inch wafer, both for silicon and for compound semiconductor. So everything in blue color is for less than 208-inch wafers, like 150 wafers, and 300 millimeter are exclusive only to 300 millimeters. Of course, this older tools also were being used right from the industry when it was using 2-inch and 4-inch wafers. So on the vertical side, you can see PVD, CVD. These are all the broadest portfolio of Applied Materials. So there are many wafer fab equipment companies, and Applied normally makes one of the largest on its portfolio. And here what you can see is a typical optical inspection equipment. Probably I'll not go through in detail into that, and also probably this slide will tell you about the overall market landscape only for the equipment wafer fab equipment companies. So all this is in blue, AMAT, that is Applied Materials. Those are the main one. And I think the light blue here is probably LAM, and then the gray here is Tokyo Electron. And here you can the lithography, this big box is ASML. So there are several various companies. That's a kind of market share and position. Just to summarize how breadth these company, wide many companies supply these equipment. And we have seen this. We have seen how the inflections are creating a new requirement for defect and also inspection challenges. So they are starting from FinFET, multiple patterning, and also 3D NAND. And the bottom line is more advanced inspection is required. And here are the example of some of the E-beam and optical equipment. And on the right-hand side, what you see is a wafer map. So typically, every inspection tool will give a wafer map. With your die, each little square is one chip, and wherever there are more defects, it will be marked red and with the wafer ID. And then when the wafer goes subsequent processing, eventually they can identify which step, which process and statistical process control, and eventually they can mark out which chips are good and bad. Right? That's a very big process, and huge number of inspection is there. Again, we saw this some time back. 28 nanometers, we had close to 750 process steps, and today. Which means each step you have to do some kind of defect review or measurement. On the right hand side, you can see what we call as a edge placement error. You can see the cut here, which is not very smooth, and you have to there are various kinds of errors, and all these have to be measured. And there has to be a sampling requirement, and there are very specific. And this is how it has been done in the industry for decades. It's not something new. This is not how it is. This is how it is being done. And between the optical and the electron beam resolution limit, we are here today around the electron beam can really go below 1 nanometer as a resolution. And whereas optical is much higher. And from 45 nanometer node, E-beam is being used fairly regularly, which is probably from the 1990s, right? And you can see the optical gaps. On the first, you see the overlay errors, because this is from between layer to layer. Direct on-device or in-die measurement is done when they do overlays between the layers, and CD is on the particular layer. Okay? And basically, you use this to measure any yield limiting dimensions. For example, on the right-hand side, you have a high aspect ratio mode where you can, the top of this is actually a via. Via means it's a hole, right? So on the left-hand side, if you see, if it is a 1 nanometer tolerance of the layer of your deposition or H layer, the metrology precision should be about 1 max. So less than 1% should be your precision. So tolerance and precision, these are entirely different, right? So even when you measure a defect, you have to classify that actually it is a defect. So For example, here is a simulation which you can really show the one that is highlighted in yellow or the defects. This is on a top view of a FinFET. On the 3D structure, you cannot see actually from the top view, but whereas on the actual industry, you can only do all these measurements from the top. You cannot cut and break and see the cross section like you do in a university SEM. You have to do it live, and from the top itself, you have to analyze and make sure what exactly how it will look on the cross section. So here on the left hand side, you can see between these two structures on 10 nanometer, it is not it is actually touching. You can see between these two, there's an overgrown AP, CG AP on these two. And the other one here, this is a bridge. This is shorted. These two, it should not be there. It should be a clear gap here. Right? So these kind of measurements and defects can be analyzed. And also edge placement errors. For example, on the left-hand side, this is an actual wafer map. If you measure all the defects and make it into a graphical representation, it will look like this, where the green and is okay and red is a higher level, where there are more, when the tolerance given, this is much higher region, right? For example, if this is how actually you see in your design, you may draw a perfect circle or a square, but actual manufacturing process, it will look like this, right? So and accordingly, the process variation will be and as you see, massive measurement is required, even to eliminate the smaller killer defects. And I'll tell you how we actually do this. I'll quickly skip this. And this we have seen the angstrom era today, what is more required, and the defect map. So this is the normal process. You do an optical inspection, you generate a defect map and do a E-beam defect review, and then bin the defects. Basically, you need a lot of statistical process control. You make a control chart, CP, CPK. This is compulsory, and the whole top 25, almost all semiconductor industry uses a software called JMP, for which also we have included in the curriculum in SRM for their masters in the nanotech department. And also there are complementary technologies, but you also have to do it really fast, and you need artificial intelligence to analyze this data and also do the statistical analysis. And here is again a limit that poses for the angstrom error challenge. For example, this is not the normal pattern roughness, and here there's a defect, clear defect. So it may not look very big when it is only few angstroms of difference. So you need to train the model to precisely find out where those defects are. And some of the defects, there's always be a questionable defect, whether is it a defect or not. Even and that is what some of the latest technologies I'll show you has overcome those. So this is a traditional conventional E-beam defect review. So for an advanced node, there are more than say 100,000 candidates. So 100,000 is about say 1 lakh from an optical inspection. So it roughly takes about 30 minutes, and say the for one full wafer, but low sampling. You can only measure 100 points. You cannot measure every single transistor, right? You can only sample based on the quality. And then there are non-defects and defects. But then new technologies, you have to do much more, right? The conventional E-beam defect review takes a lot of time to actually classify. So it takes more than 3 hours for a single wafer. And if you increase it to, say, 100 tens and thousands of candidate locations where you want to make the measurements. But then you will have a problem where some you can clearly identify defects and some are non-defects, and almost equally of non-defects is also uncertain. You don't know whether it is really defect or not. So that's where you use image processing and advanced AI algorithms to also train on the site. And these are not a common AI model which will do for all machines. It has to be customized based on every machine in the factory, because every machine is when it runs, it is going to be slightly different. Right. So this is the latest second generation cold field emission imaging from Applied Materials. So this was released during the Semicon, SPI breakfast session this year. So basically, you can here are some of the examples of defects that you see, whether it is in the gate all around. The defects are in multiple layers, but using an electron beam, you can actually see them through in multiple layers. And then even a buried bridge you can see very clearly, and also in DRAM. Actually, in this particular picture, the screen resolution is increased brightness. If you increase, you can see it clear here. Right. And then this is Applied's e-beam portfolio, and which today we don't even call it statistical sampling. We have called it massive sampling. Typically, petabytes of data come out of a single machine, and these petabytes of data has to be per hour has to be analyzed on site through the AI models and also classified, and the wafer is binned, right? And some of the basics, you probably know this, how your SEM works. A thermal source of a tungsten electrode that emits electrons, thermionic emission, and then this is a standard electron beam, how it is generated, and typically the resolution of an SEM can be more than 5 nanometers. And then of course a field emission source, it is much more sharper, and it requires operating temperature is lower, and cold field emission is at really cold temperatures, and the resolution is sub nanometers, and we can do extremely fast imaging. So what it means is the spot size is also smaller, but we have a high resolution and high throughput. There is a video, I'll not go through it, I'll send you the link. You can look at how this actually works. Basically, what on the second generation CFE on the right hand side here, you can show the same time taken with either with say a standard thermal field emission gun, and also the cold field emission Gen 1, which was released 2 years ago, and also we have a much faster resolution, and also more defects can be analyzed. And here is what I said, the AI-based review. So you sample the defects, grab the data, and then use a training data based on that particular factory, that particular equipment, that particular processor they're being, and it will train the data, and then it will do the defect reduction. So right now what will happen is it will clearly classify into defects and non-defects, and the uncertainty is kind of eliminated using this. So, and even for training, you use a design-based approach where basically right from your design data, your TCAD data, and also your how a defect should be that you can classify, and also with the actual process condition. So the actual process condition, how and where the defect is there, and also label the defects and non-defects, and eventually bin them, right? And now the new H20, the claim is now it's less than an hour. You can do the defect for completely and faster. And here are some of the classic defects. Here actually you can see a particle. Here you can see a bridge. Here you can see a scratch, again from different processes. For example, here patterning control CD measurement. You can see this particular whole contact CD measurement is wrong. The line CD could be different between here and here. It's very hard to see here, and also overlay. The overlay, it's not rightly placed. So these are all different types of defects that you can do. And traditional patterning control, for this is done normally when you do your structures are larger, which is typically at your interconnects. These are 1 micron structures, and these are typical how your wafer map looks like. And this is after etch inspection, after etching process, what is after the ADA to AEA conversion for a wafer, that you can see here. And also I'll probably skip this. Okay, this is a slide probably if you are interested in between the 450 to 100 steps. Earlier, there are much less litho steps. At 28 nanometer, you just only do a litho and an etch. So start below that, you started doing Lili, so double etch, litho etch, litho etch, litho etch, litho etch. So litho 3 times litho etch for each pattern. So now it is much more when you go below 7 nanometers. That's how your steps increase. And again, remember when I said earlier, your litho mask and removal in the after exposure and after you pattern, that's where you generate a lot of particles, because your photo mask is typically not smaller than 500 microns, right? And then the process steps also introduce variation. This is another example of that. And I'll skip this. And again, coming from statistical sampling to massive sampling. So in statistical sampling, we design where it needs to be sampled. There are acceptable sampling criteria. You have to systematically define the locations and where you can sample from. But then various designs over the years, even then you won't form the complete picture. In massive sampling, you use artificial intelligence to generate much more locations based on, so AI can be trained to see whether the defects is coming because of the chamber conditions or the process. Is it coming only at one location specific to that machine? So massive sampling can give you a much bigger and very precise picture. So that is the order of the state of the art in the industry today. So here is an example of sparse sampling and also massive sampling, which reveals actually the UV cure chamber's signature. This is how the UV cure chamber, the UV lights are placed here. So when you do massive sampling, when an actual statistical sampling, you won't actually see it is coming from the equipment itself. So people are also using this to the process engineers. It's a great tool, and you can use it to even design equipment which are better, right? And here is an example, slide which shows more measurements. Probably we are talking about defects. I'll send you this slides. And here again, stresses. Again, there is again new challenge now. We are already seeing reports in especially in the NAND when the number of layers are huge. It's more mechanical errors than stress developed, and the more stress related defects are much more coming into the industry right now. And here's a typical process control. How do you control the mean and variation in yield loss? And this I will not go through in this, but for example, how you interpret this. For example, you can see here anything beyond that 6 sigma here in the corner. Those are all the defective areas, the yield loss. Either it is too green or say too high in red, based on whatever the specification given for that particular process. So if you want to maintain the process window, you have to the yield loss you can clearly define from here. Right? And if you want to widen the process window, so you have your target, you can also see if your process is shifting. So you have 3 different processes, or maybe the same process in 3 different machines. When you measure them, you can see where is a target specification, whether it is a thickness or any other critical to quality criteria. You can see whether the process is shifting or not. That's why your SQC and statistical process knowledge becomes very, very important. And most of these processes require these kind of tools. And I will skip this. This is typical about the equipment. And also, how am I with timing, ma'am? Do we have some more time?
Yes, sir.
Okay. This is again with respect to high aspect ratio edge process, but this is typically for the 3D NAND. So typically you can see here the nitride layers for N+1 and for the capacitors that are made, Sonos or the process. But here again, defect inspection becomes very, very difficult because some of these aspect ratios come something like 1 is to say more than 500, or 1 is to maybe for 5. I think 1 is to 500. So typically, what it means is if you take the Burj Khalifa tower, the tallest tower on Earth, the aspect ratio, the width to height is 1 is to 9. So it is 9 times taller than the diameter. But then here, typical via or a hole in your NAND memory is 1 is to 500. So we have to inspect from the top. When you do an electron beam inspection from the top, you have to see whether it is tapered, whether the defects at the bottom. It's going to be very, very challenging. And whether these defects are analyzed using big data and AI, but this has been done in the industry for a long time. It's not something new. AI is not something new in the industry. As I told you, the old perceptron model is 1962. At least I know Applied Materials, we've been using this since 2010. We used to hold different kinds of names. And then today we have better models, definitely. The classification, training, and different kinds of AI models are now being coming, especially after the recent developments in the last 5 to 7 years. Right. So that's pretty much on the defects part. I hope I covered a lot of various defects and processes and also the kind of tools used. And this is my last slide. Can you see my last slide?
Yes, sir. Takeaways for students and faculty.
Yes. So this is the one slide I made for takeaway for students and faculty. So basically, most of I understand this is an FDP. For both even PhD students are there, and at least my recommendation is that you need to integrate a defect awareness in teaching and research. and integrate materials engineering in semiconductor courses, and also integrate statistical process control. So these are mandatory now, because the requirement is when this semiconductor ecosystem and the companies, when they put a job profile, they will ask you for all this. And students should learn TCAD, defect modeling, and also AA for inspection. And yield engineering is a critical career path. The yield engineers are paid very, very highly. And in SRM IST, also take this opportunity to tell you that we have this immersive nanofabrication lab. It is from the India Semiconductor Mission. We have two labs actually, one in the Department of Physics and Nanotechnology, and also one in the ECE. The one in Physics and Nanotechnology, we focus entirely on the masters and PhD students, and also the faculty for advanced work. And also, we also have a SPIE local chapter, which is recently started. And SPIE, as you know, SPIE US. And most of the lithography, for lithography, still SPIE is still number one. And in fact, most of the material that I showed you in my presentation, this is from Applied Materials presentation in SPIE events. So you can also go there and look at it. And you can also, I also request both faculty and student to join the local chapter of SPIE in SRM. And that's the end of my presentation. So this is one backup slide I had. This is basically showing what are the new kinds of materials, what people are focusing for tomorrow, means for the next 10 years. The existing materials of the existing material today is here, various process and materials. And the one in white is white color here in the font. Those are the new materials or combination of those elements.
Sir, question, this link again, sir.
Yeah, so I am done with my presentation. I can take questions and also.
Thank you. Thank you so much, sir, for your enlightening presentation and informative session. Sir, we have a few questions.
Sir, could you please switch on your video for a short time so that we take the screenshots?
How it's okay. Yeah.
You can ask
okay. Yeah, please.
Sir, and stacking multiple layers in the memory architectures, and in one slide it was given with 176 pairs of stacking multiple layers. So will it improve the storage density, sir? How is it making that?
Yeah, that's exactly it. So 176 is much smaller number. So actually what you can go into the market, I think 5 years back itself, we had about even 236 also. So you remember your SSD hard disk, today it's even come in 17 terabyte as a single disk. So earlier it used to be 1 TB, 2 TB, 4 TB hard disks. So you need to mainly your capacity. That's correct.
Okay, thank you, sir. So the 3D DRAM, will it replace NAND for certain applications, or they will complement each other? NAND is replaceable by 3D DRAMs.
I don't think it is replaceable. If you look at the memory architectures, memory has different kinds of memory with respect to their latency and speed are required for different functions. So SRAM is normally the most fastest. So usually inside your chip, there is cache memory, right? That has to be the fastest.
Yes,
so those memory cannot be DRAMs and NANDs. So DRAMs and NANDs and all used only outside.
Okay.
Usually every memory is used. It's not replaceable, but of course there will be there was a memory gap between different technologies. It will capture some of the market.
Okay, sir. Okay. Thank you, sir. So last question, sir. So from an industry perspective, the companies, how they manage the trade-off between the yield loss and the scaling requirements?
So usually, so the yield is basically for the companies which manufacture. So these are the companies basically either the foundries or the fabs. So this they jointly work with the equipment manufacturers, because the equipment manufacturers normally have the technology for the processes, right? So usually it is a long development time over several years, maybe decades sometimes they work on it. And also depending upon their design specifics. So the yield is basically, normally let us give an example. Right now we are in India, we are starting a 28 nanometer fab at Tata in Gujarat. So the fab is under construction right now. So the ones when the fab is completed, the equipment move in, there will be a ramp up. So the first wafer that goes in, it will not produce a good yield. So they have to optimize it continuously for several months together. So there will be an army of engineers from all the companies working there. There's a huge amount, almost they'll have to wait for 1 or 2 years to slowly increase the yield, because the yield has to be much higher than higher 90s to have the factory to run profitable.
Yes. Thank you very much, sir, for your delivering such an excellent and thought-provoking session. Your insights were truly enlightening and have provided us with a deeper understanding of the subject. We sincerely thank you for your time and effort you have taken to share your expertise with us. On behalf of the organizers and participants of this ATAL FDP Semitech 25, we extend our heartfelt gratitude for your valuable contributions. Thank you, sir.
Yeah, thank you very much. And also, I also shared my LinkedIn profile so people can also write to me. If you have any questions you could not ask in this, you please do in the chat box and also reach out to me.
Yes.
Thank you, sir.
Thank you.
Thank you. Dear participants, come to the conclusion of the third day sessions. Please start writing the reflective journal. As it is told, you have to identify 3 key concepts and the implementation plan from the 6 days program. So you please note down for the last 3 days, and hope you have identified at least 1 or 2 by the end of 3 days. And Sumitra ma'am, any other announcements?
Ma'am, attendance link is posted. The participants are requested to fill the attendance. Thank you. Thank you.
Please do not forget to put your SRM ID in the feedback in the attendance link. And dear participants, tomorrow we have sessions from 6 to 7:30. Dr. Swami Datta from IIT Madras, and then followed by we have Sir Michael Corel, Department of CNSS, Mexico. So tomorrow also we'll have nice engaging sessions. So I request all of you to kindly join on time and enjoy the sessions. Thank you.
Thank you.
Ma'am, can we wind up the meet or shall we wait for some other more announcements?
No, sir.
We can wind up.
Yes, sir. They were asking for attendance link.
Attendance links are already shared in this chat box here.
The people have started giving their attendance.
So, madam, participants are asking about the reflective journal announcement.
We will post it in the portal.
WhatsApp group or?
We will give a sample, sir.
Yes. Sample will provide you on the WhatsApp group tomorrow. So you can see the sample and then start preparing for those journals.
The necessary information will be posted in WhatsApp group.
It is a requirement from AICTE, so all have to write that journal. After that, only you will get the certificate of competition. Okay.
Thank you, sir.
Thank you, sir. Thank you.